Hello friends, good morning. This lecture is going to be on expectation. So I am going to explain the concepts of monotone convergence theorem, its proof, and expectation of a real valued random variable. I have already uploaded a note which you can see now, titled Probability, Random Variables and Expectation. It's a 6-page note, but the content it covers a very important and elaborate topic in probability theory. It is summarized. It is written in like a research paper in a summarized manner, but to explain it takes some time. So without delaying any further, let us just revisit this one. I think we have spoke about the monotone convergence theorem. The monotone convergence theorem, where is it stated? Fattus Lemma. So here it is. The monotone convergence theorem states that if I have a sequence of non-negative valued monotonically non-decreasing random variables, then limit of expectation is expectation of the limit. So here the conditions are non-negative and non-decreasing. Non-decreasing means if I take any two random variable xn and xn plus 1, the one that has bigger suffix will dominate pointwise. That is, xnw is less than equal to xn plus 1 w for all w in this sample space. So here is the proof. You see, here I like this proof because it uses several properties that we have discussed earlier. So how do we prove this? The first we show an inequality, that is, first see that this expectation of xn's is a non-negative non-decreasing sequence of real numbers, non-negative numbers. Why? Because xn's are non-decreasing. So by this monotonic property, as you can see, property number 2, if x is less than equal to y, and this inequality means pointwise, x and y are two random variables on the same probability space, then expectation of x is less than equal to expectation of y, and of course this is non-negative. So by using this property, we get that if you have a sequence of non-decreasing, that is xn less than equal to xn plus 1, if you have a sequence of non-decreasing random variables on a probability space, then their expectations are a non-decreasing sequence of numbers. And what do you know about the non-decreasing sequence of numbers? That their limit exists. Now that limit may or may not be finite. That is another story. So and another thing, you see that each of these xn's will be less than equal to supremum of xn's. So why supremum of xn's? Because this is a sequence of point. So this is a sequence of non-negative valued functions. So at each point you can look at it as a sequence of, just think of it like a sequence of non-negative and non-decreasing numbers. Then each xn is less than equal to the supremum, and that is the limit, because this is a non-decreasing sequence. And so one part of the theorem is obvious. So you see the limit of expectation, if I take now expectation, these expectation of xn's are a non-decreasing sequence, so they have a limit, and so that limit is bounded above by the supremum, provided it is finite. So what do you know about convergence of non-negative monotonic sequence of numbers? You know that if I take a sequence of non-negative non-decreasing real numbers, then it is then there are only two possibilities. If it is bounded above, then it is convergence and converges to the least upper bound, and if it is not bounded above, then it will diverge to then it will diverge. So limit will be infinite. So by that logic, so this limit of xn's exist, and they will be dominated by the right side, the expectation of the supremum, which is the expectation of the limit. So one part is proved immediately, that expectation, what you have proven is that limit of these expectations is less than or equal to expectation of limit. That follows immediately just from the fact that xn's are non-decreasing, and you are using the property of monotonicity, property 2. You are using this property 2, and the fact that xn's are a non-negative sequence of real numbers. So one part you get immediately. To prove the other part, what do I mean by the other part? Now if you want to prove that the limit of this expectation, limit of this sequence is greater than equal to expectation of the limit, then you get the equality, right? So if you want to prove x is equal to y, you can prove it by x is less than equal to y, and y is less than equal to x, then x is equal to y. So to prove the other part, we take any non-negative simple random variable dominated above by x. Now what is this x? By x I refer to this pointwise limit. So limit of xn's I am denoting by x. So now define a set like this where c is a proper fraction. Now I leave it as an exercise for you, that since xn converges to xw, therefore for every as you increase n, this set would increase to the whole set omega. Why? Because this is due to this fact. Here I have noted down. It is because of this property 2 in remark 5. So now what is what is expectation of xn? Remember, xn is a non-negative valued random variable. So if you multiply any non-negative random variable by an indicator random variable, then obviously then you get another, then xn will dominate this product. Why? Because outside this set it will be 0 and xn is always non-negative, and inside this set xn is equal to so the xn and xn into I and w will be matching. So you will have this relation between the random variable, and the expectations will also respect that. So expectation of xn's will be greater than this, and on this set by definition what happens is, for each w in omega, xnw is greater than cn into so again I get a third relation, that c into, this is again by property 2 monotonicity of expectation. So it's c, so I have skipped one step, it should be greater than equal to expectation of c into g times this. Now c comes out, that is again follows from the definition of expectation, that if x is a non-negative valued random variable, then c is a non-negative number, then c into x, expectation of c into x is c times expectation of x. That is something that follows immediately from the definition. So I have this. So now if I take, so I have got two non-negative sequences, one dominating the other. So supremum of one cannot be less than the supremum of the right side. So this is the relation that I am using, that and here it is a increasing function, increasing sequence of simple random variables. So expectation is a non-decreasing sequence of numbers, so their supremum is the limit. So I take this, and this I am using the property 6. What was the property 6 of simple random variables? Property 6 says that if in is a increasing sequence of events increasing to a omega, whole set omega, then your limit of this expectation is expectation of x. So that is what is an's here. In my proof, an's are your omega n's. These are the an's. So this is where I have said that this omega n increases to omega. So I am using the property 6 over here. And remember, G is any arbitrary non-negative simple function dominated by x. So now if I take supremum over all such G's, so if I take the supremum over all such G's, what is that? So then supremum over all such G's is expectation of x. So I have gotten this. Now you may certainly be surprised that where that C has gone. So here is the logic, that the number one logic that I have written in the number. If suppose x and y are two numbers such that x is less than equal to y for every C between 0 to 1, then definitely x is greater than equal to y. So this is something I leave it as an exercise for you to verify. So I have used that here. So this completes the other side of the proof. So you get a monotone convergence theorem. And if the importance of the monotone convergence theorem that I told you is that you get an alternative definition of a expectation of a non-negative valued random variable. That you can define expectation of x to be the limit of expectations of an increasing sequence of non-negative simple random variables. Now the third most important result in this context is called the Fattus Lemma. And now Fattus Lemma tells you that if you take a sequence of non-negative simple functions, so here you can see I am giving up the condition of monotonicity. So I am simply saying that I am taking a sequence of non-negative random variable. It is for simple, but it also holds for any random variable. Then expectation of lim_inf of xn is less than equal to lim_inf of expectation of xn. So it looks a bit peculiar and hard to remember, but I hope you are familiar with the concept of lim_inf and lim_sup of a sequence. Do you know what is the difference between the lim_inf and infimum of a sequence and lim_sup and supremum of a sequence? If not, then I would suggest certainly that you please refer to Bartley and Shepard real analysis to revisit those concepts. Now to brush up your memory, suppose I have a sequence which starts with, let us say, 0, then it is -1 + 1 -1 + 1 all the way. Okay. Okay, sorry, not with 0. So let us suppose I start with a sequence which is -10 and then -1 + 1 -1 + 1 all the way. Then what is the infimum of this sequence? Certainly this is bounded below and the infimum is -10, because you don't have any number so for all n, xn is greater than or equal to -10. So -10 is the infimum. But is it the lim_inf? Certainly not, because here what I said, first term is -10, then it is -1 + 1 -1 + 1. So here you see this sequence has the infimum is -10, but there are two limit points, namely -1 and +1. So why? Because -1 is also occurring infinitely many times and +1 is also occurring infinitely many times. So we can say that there is a subsequence that that converges to -1 and there is a subsequence that converges to 1. So there are two subsequences, so convergent subsequences here. So there are two limit points and the smallest limit point is -1, so it is the lim_inf. So lim_inf means for a bounded sequence, you know, for a bounded sequence has at least one limit point, so the smallest limit point is the lim_inf, and similarly the lim_sup is the largest limit point. Now for a convergent sequence, the lim_inf and there is only one limit point, and so the lim_inf and the lim_sup are equal. So I'll stop here today. So this is now how do you define lim_inf and lim_sup of a sequence of function? Well, in the same, just extend this concept point wise. So you remember xn is a function defined over a probability space omega. So for take any